Good morning, afternoon, evening, everyone. Thank you for joining us for the SEG Near Surface Technical Section Student Subcommittee's third Python workshop. Today, Joshua Pavadi and I are going to be talking through a few aspects of using data frames and geodata frames, basically database management within Python. Starting to talk a little bit about how to use some of the different packages that exist. Yeah, there'll be some presentations. I'll be throwing in some example codes and data sets that I'll be throwing those in for people to mess around with and get familiar with. And yeah, if you have any questions over the course of the presentation, please drop them into the Q&A section. We will try and leave a little bit of time at the end of each presentation to cover questions. But anything pressing, we might take a quick second to try and answer. Thank you again for joining us. Lori, did I miss anything?
No, I think that's good.
Okay, yeah, hi everyone. Good morning, afternoon, and evening, depending on your current location. So I will be taking us briefly through just general introduction on database while Chris will handle more of the technical part. So Laurie, let's go ahead. So generally, we're talking about databases. We're talking about an organized collection of structured information or data. Typically, we store this in the form of electronic format. So what we're looking at is you have a set of data. It could be different types of data. Either you're within the geoscience domain, you have different types of data extension that are coming from different sources. Probably, let's say you have well log information that's coming out from drilling data. You have seismic data type and different types. And now most of this data now are presented in form of tabular forms. For example, if you look at typical well log information and so on that has to do with depth information, it comes in form of tables where you have several depth types, and then you have this each of the sensors with the different information. So it comes like in the form of an Excel sheet. Now, what do we do with this data? It's been stored within a database. And basically, when you store this database, all you're trying to do at the end of it, it's your ability to be able to extract this data, to be able to transform this data and load it in such that you can be able to generate some level of sense from it. I put in business intelligence here because at the end of every project you're working on, either within the academia, within the industry, at the end, it's how much information can you derive from this particular data that you are trying to interpret, you're trying to do a lot of models with. Now you can present the information in form of more technical formats where you're based on your the objective of the project and the audience you're going to deal basically with, or you can make it in form of graphs where you're coming from a technical background, but you need to speak to other people that do not understand what you really trying to do generally. Let's hit it, Laurie. So generally, there are different types of database management system. Now we have the first tier architecture, we have the second tier, and we have the third tier architecture. Now, when we have the first tier, what it means is you have a particular database where this particular data has been stored, and you have only one person having access to it. So typically, for example, it's you have your own laptop system where you have specific files that you've saved within specific folders, and you alone can have access to those local files because it's just within your computer. While the second tier architecture is where we have other people can have access to this particular database. It could be two or more people. And on the third architecture, now we're dealing with scenarios which are commonly used now, where you have a database and we have a server right at the middle, which interface with the applications which you're having access to. So for example, let's take example where there's a database, you have, let's say the Google Drive, or you have, let's say Dropbox, and where every of the items you're trying to save, it's online, but then there's a particular local database where all this information pass through. So everybody can have access to this specific data at any time, given time. And that's one importance about it. Now, when you trace back the history of databases, you trace back as far as when Microsoft came up with generally about database in 1960s. And then we've seen this level of transition where we have relational databases came into play in 1970s. And this continuously move, and we see the introduction of the SQL, we see the introduction of NoSQL, and currently we're talking about rise of no-code application, APIs, and so on. Typically, when you look at, for example, typical example, when you do a lot of machine learning models, you keep hearing about, oh, we need to build an API because we need to deploy this particular model so that it could be useful to other people. So basically, we'll look at different types of these databases. So the first we'll look at is the relational database. Let's go ahead, Laurie. So now relational databases are those data types where we get to store them in forms of tables where you have rows and columns. So typically, like you have your Excel sheet where if you are a businessman and then you have a lot of customers coming in to buy a lot of things from you on a daily basis, and then you decide to put in records for all this that's happening. So you put them in form of an Excel sheet where you have the names of customers. First, you have like a form of index which captures how many, the numbering, 1, 2, 3, 4, 5. You have the names of customers, the items they bought, and so on. Now, but you see in the typical Excel sheet, you have a lot of information in several rows and columns. So now, but in the case of relational databases, what we see is you can break this big Excel sheet into chunks of tables which can relate to each other. For example, when you look at the top right corner of the screen where we have information on customers, we have information on the employees, the orders, and the product. Now, but each of this table, you will say that within the customer table, it relates to the table on the orders with a unique ID we call the customer ID, while the ID under when you compare the tables on orders and product, it can link up to the table with the products with the unique ID called the product ID. And then you can also link your employees with tables. And now this is important for you to understand this because when you're doing a lot of SQL, and then you have to use functions like join, create table, and so on, and you have to link 1 or 2, 3, 4 tables together, all you're going to do is you have to look out for unique IDs that are connecting one table to the other tables. And we've seen an example of this. Like I said, you have the structured query language, the SQL, which we'll subsequently look at during the course of the presentation. All we're trying to do is we establish a lot of links of how this data can be accessed easily in forms of which they come in form of rows and in form of column. Now, other example of data types, Laurie, let's go ahead. We have the not only SQL databases, so we call it NoSQL. Basically, these are non-tabular databases. We get to store data differently in a different way than the relational database, which is basically coming in rows and columns. So we have different types of data that can come, which it might not just be a type of data that we see typically in forms of numbering, rows, and column, but then the NoSQL accounts for other data types that we have generally. An example of some of these databases is I've put in some feature. We have the Neo4j, Cassandra, Mongo, DB, which could use a lot of this information. And it's just typically where you see like companies like Netflix, companies like Facebook, companies like some of these big IT companies. Now, they tend to have a lot of information from users on a daily basis. Probably if you're using Facebook, you have information about different chats that are coming with people, different posts, different this. All this information go into a particular database where they are being stored. So what we see in the typical NoSQL database, Laurie, we can go ahead, is we just a step backward here. Thank you, Laurie. Now, these data are being stored in form of keys and values, so which is a bit different from the way we have seen the table where we get to store SQL databases, where in the keys, it relates to specific unique keys where if you want to access a particular range of information, and the values could be an assemblage of different types of data. Like, for example, what we see on the first row there, we have name of the person, we have the age of the person, you have maybe the sex of the person, you have different information about the person. So the value might not just be in a typical, just like what we see in the SQL database, where you have maybe a unique key and then you have only one single value attached to it. But here for the value, you have different types of information about the particular unique key that we are dealing with. So when you look at the advantages and disadvantages of the SQL databases and no SQL database, Laurie, go ahead. Now, we've seen in terms of scaling, most especially, that for a typical SQL database, what we see is we only have what we call vertical scaling, and in the NoSQL, we have both the vertical and the horizontal scaling. What am I trying to say? If we're talking about scaling generally in database, it's typically we have a particular, let's say you have a RAM size, which is, or a disk size, which is 1 gig in your system. And then that particular 1 gig is completely full, and then you need to add more data. What shall you do? Now, a typical, what we see is, Laurie, go ahead. We begin to have, it's just typically like you're having a building of an upstairs building you're building. So you have the first floor, you need to add data in more RAM size or more compartment to it. You need to add to it like as if you're adding different stages on the type of building. But what we see in a typical horizontal scaling, it's your ability to be able to spread this information, not just adding RAM sizes. Thank you, Laurie. So not just we adding just RAM sizes vertically, but we can horizontally bring in more servers into the system by merging this entire information. That's why NoSQL database are more advantageous when it comes in terms of most especially scaling information. Go ahead, Laurie. Now, the next step we'll look at its object-oriented databases, where we have access to this database. We tend to manage them, but it tends to use different principle. We look at object-oriented type of database, where this deals with using both the principle of object-oriented programming, where the data is represented as objects with attributes and method. And these databases are suitable for application with complex data structures and relationships. So beyond just the type of data types we use for the SQL and NoSQL, if you want to use other databases that could host a lot of complex type of data structures, which you tend to use different object-oriented programming to have access to this data, then you can go down to use typical object-oriented databases. Example, we see the DB4 object by Varson, Gemstone, and the object DB. Go ahead, Laurie. Yeah. Another type we can see it's when you're dealing with the type series databases. Now, typically when you're having a lot of time series data, probably you're working within, let's say, in weather focused, where you deal with information in time. You're trying to see what happens in the past, and you're trying to make a lot of insights to currently what you see. So this is a type of database you can save this. And typical example we see here, we look at the application around the Internet of Things, where you have a lot of sensors that could be attached. For example, these sensors could be installed on the ground. It's in terms of earthquake monitoring, it can be able to monitor a lot of seismic movements here and there, or for construction basis. And this is always recorded in time, and your ability to be able to store this information in time, to have access to all this information in time. Now, like I put there, it involves timestamp data. Now, when we talk about timestamp data, we're dealing with both the date and we're dealing with both the timing. So you have all information about when it occurred, at what time exactly at each of the second, and you can be able to have access to this data and make sense at the end out of it. So example of this we see is Prometheus, Influx, DB, and so on. So there are several types of databases. This is just general introduction to this, and you can go ahead to look at this online. There are a lot of resources on this. Now, an introduction, generally, when we come to database management, what are we trying to do in terms of database management? Or you can go ahead to the next slide. Now, database management refers to the process of efficiently and securely storing, organizing, retrieving, and managing the data within the database system. So what we see is you have this set of data that are copied from different sources. Like I said, example earlier, we in terms of geological type of data, we have different types of data. It could be information you got from seismic seismology aspect. It could be information resistivity information. It could be the information you got from drones doing a lot of surveys in the air, and taking gravimetric data and so on. And then it could be you drilling down to look for different resources, and then you're able to get a lot of well-logged drilling information. So you have different types of sources coming in. Now, your ability to efficiently store this data, to organize them in a sense where different people can have access to this data to use it. Now, this data could be a lot. I mean, it could be a lot, and currently I think this is one of the things that derives the current trend in data science, machine learning, data engineering, careers in cloud, and so on, because you have a lot of data that have been stored over the years, but we are yet to make a lot of sense out of this data. And now companies are spending a lot when it comes in terms of understanding this, a lot of information they have, and how they could transform this data and then bring out some sense which could be profitable for their businesses. It could be profitable generally for research and technology and so on. So around data management, you talk about different aspects. You look at data transformation, you look at data governance, which has to do generally with laws around how data should be handled. And on a daily basis, you could imagine the amount of data that have been derived from, let's say, different social media platform. Now, there must be this level of governance, some level of restriction on how the companies that are harnessing this data, that are retrieving this data, on how they can use it. Because on the personal, a lot of personal information about you and me are out there being retrieved by a lot of companies. So if there are not laws around that could control how this data could be used, sometimes on the negative aspect, a lot of information could be used for the negative purposes, but on the positive purposes, companies can tend to use some of this information to be able to derive traffic to the business, to be able to make a lot of profits for their business and so on. Now, we looked at the different architecture. What are the databases? Now, you determine based on your need as a company, as a researcher in the academia or in the industry, what are the specific data types I deal with, and what are the type of databases I should use for my own company. So, and you have to look at your resources. Do you have the required financial resource, required instrumentation and so on to host all this data, or should I just go for the option of just hosting my entire data set within a cloud based type of database where other companies could be responsible in managing this type of data for you, and then you just you are not bothered with where to store and so on. Other people can manage that, and you pay for services. And how are this data being retrieved and so on? So this encompasses everything that has to do around database management. So beyond just having data from different sources, how are you able to get this data? Are you able to accurately and to accurately access it and in the right way? And how much of the access data that you have gotten now, how much of information you can derive out of it? So a lot of things are encompassing around when it comes to database management. So there are several advantages when it comes to data base management systems. Now, one, it's we look at, go ahead, Laurie. We can see when it comes in terms of data migration, your ability to be able to move data from one database easily to another database, or from the database to the users. You can talk about data security. How secure is your database as a company, or if you're as a researcher, how much secure is your data? You talk about advantages around decision making, house simplicity, data privacy, data sharing, decision integrity, data concurrency, low maintenance, how multi-asset support, that is for a lot of people having different access to this information at the same time, and then the system is so scalable that it could actually no matter the amount of pressure coming in from different sources trying to acquire this data, your system is built enough to be able to withstand the amount of pressure that can come in. So a lot of information and a lot of benefits are there when you are trying to manage your entire database system. So Laurie, you can go ahead. We basically, for today, we will be looking at generally different tools that have been common tools we see that are currently being used generally in earth science. A lot of them are all open source, and you can find them out there if you want to work with any of them. Shapely, Fiona, GeoPandas, GeoPy, Catopi, QField, GDAL, and so on, which are either used for the purposes of mapping, for the purposes of having building general information around earth science, for monitoring, and so on. So, but for today, we'll be looking at the GeoPandas alongside the Python. Go ahead, Laurie. Alongside Python, SQL, and so on. So generally, the GeoPandas is an open project which has been built in the aspect of trying to help with geospatial data using Python generally. So the GeoPandas extended data types that use pandas to allow spatial operations on geometric types, and Chris is going to talk more on that. So I put an example here where you can see typically where you can display geospatial information on like a sort of a map where you have different, which can define different information on what you're actually looking at for specifically. So next slide, Laurie. And so, like I said, Chris will go ahead to look at do some hands-on tutorials on the database management generally. We'll look at the use of Python, different Python libraries. So beyond using the typical libraries that we know for in Python, beyond your pandas, NumPy, depending on the project you're actually handling, for those doing machine learning algorithms and so on, you have different SciPy and so on that you can be able to use. And then we look at how we can use SQL generally, which is the most common type of database management, which we see where you can connect different tables for relational purposes. You can use different functions. And there are a lot of resources which you can use this if you're trying to learn how to use SQL. And then we'll look at the GeoPandas. But generally, it's important as earth scientists to have substantial knowledge about how these tools operate and how you can use generally these tools to make your work easy in terms of accessing data, in terms of trying to use basic coding here and there to be able to do some sort of models in case you do not have access to some of these expensive softwares that are probably industry based, but if you can find a way to code these things yourself. And it's important you learn this and just spend time on a daily basis to be able to do this. So I think I'm going to stop here so that we have the bulk of time to do the hands-on tutorial. Thank you very much. Yeah.
All right, thank you, Joshua.
Yeah.
So we do have a question from Gabriella asking what kind of SQL database is mostly used with geophysical data, such as in oil and gas. It says usually the size of seismic acquisition data is so big and has many components. Do you happen to have an answer for that, Josh? Or
so she's asking the specific type of SQL database for geophysics.
Mhm.
I'm not sure I really know if there's a specific name for that within the industry, really. But I believe there should be not necessarily a specific name as such, but then SQL is being used within the industry to be able to access all this data.
yeah, I know. I can shed a little bit of there's a very faint amount of light on it. I really don't have any experience with the oil and gas industry as far as like data management is concerned, but I know that some companies are starting to move towards using the Microsoft SQL Server kind of like software package. So as far as like strict SQL databases are concerned, I think that's definitely the kind of becoming the most common one. But yeah, like Joshua said, there really isn't a like hard and fast like this is the industry standard for SQL. It's more something that more companies are starting to like make their way into and start to incorporate more into their data management, whether it be through an actual SQL software like Microsoft SQL Server, or whether through incorporating Python code into it. But the SQL one or no SQL type. Yeah, so I think the Microsoft SQL Server would be the SQL type, I believe.
But at the same time, I think others they could incorporate probably NoSQL because it depends on the data type.
Okay, yeah.
So if it's not a type of relational which comes in terms of rows and columns, then if the data is coming in the form of a different type, then NoSQL can suffice for that.
All right, so let's get things going. So I'm going to drop a link to a shared Google Drive folder that will have both we'll have this presentation, the code that I'll be kind of like going through to give some examples of how to work in pandas, and an example data set, or an example yeah, I guess an example data set to work with. So let me drop that into the chat quickly. For anyone who's so trying to like catch up with some of the past two Python workshops, there are folders to share data and presentations from the other two workshops here as well. So feel free to peruse and use at your leisure. So let's swap that around. So a quick kind of correction to what Joshua was talking about at the end of his presentation. Due to the kind of time constraints, primarily just going to be talking about using the pandas package and the GeoPandas package as far as database management and manipulation is concerned. If we had the time, would have try to delve a bit into using SQLite, which is an SQL based package that's available for Python. But unfortunately, it's kind of due to the timing of everything. It's primarily just going to be pandas and GeoPandas, and it's kind of talking about general database management in Python. So what is the pandas package? So pandas is an open source Python package. As with any Python package, it's open source. Its main purpose is to introduce easy to use and easy to read data structures to help with data analysis. So since it doesn't quite follow as structured a as structured an element as databases, as like SQL databases, it puts forward this new type of element called or new type of object called a data frame. Data frames are essentially just specific to, like, kind of more or less specific to pandas. It's just a way for it to be like, hey, here's a little bit of a loose interpretation of a database. Its main draw is that it's able to very easily kind of sort, query, and manipulate the rows and columns of the data frames, either by their index or their label, or by using Boolean logic. And so we'll be talking through a good amount of that over the next bit of time that we got. So to kind of give a little bit of a breakdown on the difference between a pandas data frame and a kind of more SQL adjacent database. So as Joshua talked about when he was talking about the databases, right? These are very efficient structures, and they maintain that efficiency because they're pretty, depending on the database you're working with, they pretty much have to be pretty rigid as far as the type of data type that goes into each column. If you can't all of a sudden you can't have a column that's mostly float numbers and then throw in a bunch of strings later on and like still expect to have that same efficiency. So databases have a very rigid requirement that you have that same data type within the columns. Data frames, you can mix and match. You can concatenate, so you can basically append to your multiple data frames together, and with that, your column could now start to have integers, floats, strings, and what it'll do is the data frame is going to represent, when you call that column, it'll represent, it'll see what object type, what data type is able to represent all of the rows within that column. So if you have a bunch of integers and floats, it will say that it might just read out that if you call that column, that's gonna be an integer, because at the very least there's an integer within all the floats. The integer is just a rounded float, right? Meanwhile, if you have like numbers and strings and all that fun stuff, it's going to give you the data frame object or the data frame data type as an object. There's something super vague that says something exists within these rows. Different data types, but it's an object, right? Data frames, they're definitely more optimized for ease of use. They are a lot more kind of quote unquote like plug and play, where you can bring in just about any structure of data file into there and figure out a way to get it presented in the way that you would like. Databases, once again, they're really optimized for very efficiently handling massive data sets. Data frames, very loose structure. You can have just your basic row and columns. You can assign labels to your rows or columns or just keep them as numbers. You can have multi-indexed data frames where you have some columns that you basically have like one tier of column label and then another tier of column label that maybe applies to multiple columns. So it allows you to kind of define the structure of your data frame depending on what kind of data you're working with. Databases, that's kind of explained, pretty strict structure, right? You can't really get to this tier level of multi-indexing, which is makes sense if you want to kind of very rapidly move through a bunch of data points, but it's a lot more harsh when it comes to trying to get used to figuring out how to construct and build a database. Last thing, data frames. Basically any function that exists within adjacent Python packages, anything in NumPy, SciPy, Matplotlib, whatever, can be used with data frames. You can apply, as an example, you can apply like a function that turns all the rows in a column into strings, or converts them into a specific object for some other package. Meanwhile, databases, right, they with like more SQL adjacent databases, you don't really have too many options as far as the list of functions you can choose from. Like, you still have a good amount, but it is limited. It's just very efficient with each one of those functions. So when it comes to creating data frames, there are a few ways you can go about it. I'm just kind of outlining a few of the potential functions that you can use. So as you can see to the left here, this is kind of an example data frame. You have your row labels, your column labels. If you didn't specify anything when you uploaded your data, these column labels would just be 0, 1, 2, and 3. And then your data within each point, right? If you have an idea, if you have some specified NumPy arrays or lists that you want to build into a data frame, you have the standard pandas.dataframe function, allows you to specify what data you want to throw in, specify the labels, all good. The next three are used depending on the type of file type that your data exists within. If you have just like a standard comma separated value file, you can read that in, define or specify in the function that first row is headers, so it can interpret the column names based off of that first row in the file. You can specify the data types for each column, so on and so forth. You can specify how many rows you want to import if you know that it's only like the first 3,000 rows that actually have data, then everything past then is kind of more like formatting stuff that gets exported when you save your data. You can specify, all right, only read the first 3,000 rows and go with that. The read FWF, that's fixed width format. That is primarily just used if you're dealing with some kind of more loosely structured text files that maybe don't have as obvious a format and how many columns exist in each one. So like if you have files where you have the first, like I said, the first 3,000 rows are 4 columns and the next 8,000 are 6 columns, you can kind of start specifying the structure of your data file using read FWF. Then with read Excel, this is just handy if you have a data file that has multiple sheets. So you can import the Excel file as it is and specify to create a data frame for each sheet, or specify which specific Excel sheet you want to use. It's just basically the read CSV function, but more specific to Excel files. One thing I will always tout the benefit of, because it has helped me countless times, will continue to help me until the day that I pass from this earth. API references. Every single, or the vast majority of Python packages, pandas, GeoPandas, NumPy, SciPy, Matplotlib, even as you might have seen if you were at the other open source software workshops with like ResAPI, eMagPy, GPRPy, they have these API references, which essentially act as a document to outline, here is what each function does, here are the different variables that you can call and specify within each one, here is what each variable requires as an input, and here's what the function will return. Anytime you are trying to figure out, wait, how does this function work? Just type in, if you're stuck on a specific pandas function, just type in pandas, the name of the function, and a page will pop up to say, yep, here's that function, here's the descriptions of it. And then, yeah, aside from this, Stack Overflow forums in general, those kind of tech help, coding help blogs, great place to see people who have made the same mistakes or stuck in the same issues, and have people who have gone through those mistakes before to correct them and see how they can fix it. So when it comes to selecting data in pandas, you've brought your data in, you have your data frame. So I'm gonna be switching between data and data just the entire time through this, so apologize. So when it comes to selecting, you have a few methods that you can use. So if you use so df here, this stands for whatever variable you've assigned as your data frame. So if you import your data and you just call your data frame data, like, okay, this, if you call your data frame, right, then this would be dataframe.ilog or dataframe.lock. If you imported your data and you called it cheese, it'd be cheese.ilog and cheese.lock. So iloc just means that you are locating a point based off of its index. So index, once again, is kind of getting back to the different labels here, but specifically its position within the data frame, not with regards to any specific kind of labels. So you can see that I have a data frame called data. I use .iloc, got all the rows in the fifth column, looked at the shape of it. So how many data points are within that column? Got just over 10,000. And now if you do .lock, which now you specify which column you want based off of the column label. So if my fifth column is my resistivity values, then you do len your data frame name .lock, specify all the rows still, and then in quotes, because this is a string, you specify the name of the column. That's about the same thing, right? Another thing you can do that I'll show in the example is you can just do the name of your data frame and then square bracket and the name of your column. So you could do just data square bracket row meters and then close it without having to specify the little colon here to specify selecting all the rows, and it'll just give you that column anyways. Additionally, if you want to select a random sample size, you just have the name of your data set. Once again, here you go. You got, we're just grabbing the column for the resistivity, and then .sample, and then however many samples you want to take. Sure enough, our sample data set has 50 points. Good if you just want to do some random sampling as for any statistical stuff. And then finally, Boolean indexing. So Boolean indexing is a very common way of trying to select data based off of certain conditions, right? It's basically saying return any values that relate to this argument. So in this case, right, if I want to get any, if I know that any resistivity values I have that are below 0, like that shouldn't be happening. So data above 0, your your data frame name dot lock, square bracket, your data frame name again, which column you're trying to build the relationship for, and then greater than 0 in this instance, right? And so if you look at length of that, you see that it did remove about like 440 points that were below 0. There are a wide variety of things you can do to, of Boolean relationships you can use to try and figure out, to select specific data points from your data frame. So it is a very handy tool in that sense. It comes to querying data frames, right? Querying just meaning that you are kind of in a similar situation to the df.lock down here, trying to figure out where, try to pull data from a data frame that meets a certain condition. We talked about df.lock, right? As you saw here. So what I'm doing is I specified some specific range of resistivity values, and now I'm just applying that filter to my data frame. So you're using the dot lock, specifying the column, and then dot between row range 0, so that the first value of my range and then the second value. So what this will do is this will look through your data frame and see and return any columns where your resistivity are between the resistivity values are between those two values, right? And now I'm just saying how many data points we got removed. 629. Cool, love it. df.where, pretty similar function. The main difference between .where and then using this Boolean indexing up here is that you retrieve an output with the same shape as the input data. And so if you're dealing with certain processes, or you're, have certain processing steps where you need to have maintain the same shape of your data frame throughout the entirety of it, then that's where you would want to use .where as opposed to .lock. .lock is just going to return just a data frame of just the points that meet that relationship. So if you have 629 data points that got removed, and you started off with, let's see here, there we go, with 10,706, right? So you have just over 10,100 or around 10,100 data points left. It'll return a data frame of that size. Meanwhile, if you did df.where, you're going to have a data frame of the exact same size as the data frame that you started with, except now anything that was deemed false, that did not apply to that Boolean statement, is now going to be marked as NaN, so a not applicable number. And then you have df.mask, which is just the opposite of .where, where it will return the data structure the same shape as what you input in there, but this time it looks for values that this time it's returning values that are outside of that don't apply to that Boolean statement, right? So if you want to look for data frame for points of data that were outside of a specific range, outside of this range that we filtered with before, and just keep those ones, the ones that are outside of the range. Then you can use mask, and that'll basically do the same thing as where, except you will, like I said, have the same shape, but now anything that does apply to that Boolean statement will be flagged as NaN. df.query, similar situation with .lock. The main benefit is you get to write it out as a string. It goes off of a specific kind of series of Python based or NumPy based string equivalences to different types of Boolean functions. So you can see here the data range I was going with was 0.5 to 100 ohm meters, as opposed to using dot between and getting all Python-y about it and getting the two endpoints of the range. You can just put it in as a string and say, all right, your column of row in ohm meters is greater than or equal to 0.5, less than or equal to 100. And there you go. Removes the same amount of data points. Finally, you have df.unique, which just returns an array with all the unique values. And so if you wanted to remove any duplicates, or you want to only have unique values for some reason, I'll give you an example later, then you can just use .unique and get all of those. So one of the big things I kind of want to stress here is that there might come times when you're dealing with a lot of when you want to get very specific about the kind of Boolean logic that you want to use. You want to be very particular with the data that you're filtering out. You can start just chaining Boolean operators together, but there are, as with anything in math, for instance, there is a precedence that exists with what Python will take care of first. And so I have this list here. I copied the presentation into that folder. And so I'm not going to go over each one because time, but just if you're trying to specify a very specific filter to use on your data and you're seeing that it's not spitting out the right thing, just double check how you have things set up in accordance with this list here. See if maybe Python is analyzing and going through something, some term before you intended it to, right? Maybe you wanted it to apply, you want to have that bitwise OR operator happen first before going with this other AND function, but the way you have it structured, it just didn't, it got things all flipped up. Just take the time to carefully plot out how you want to apply that filter, double check with this table, and see if maybe that's where any issues are stemming from. So when it comes to manipulating data frames, pretty straightforward. They're able to any arithmetic operations, you can just take the let's see, something again. Let's see, Lori or Josh, can one of y'all send or yes, are you talking about the whatever? I'll say the link to the recording won't be available until after the stuff again, and that'll be in the same playlist with the rest of the Python recordings. Let me get that thing going again. There we go. All right. All right, so any basic arithmetic operations you can just throw in right into the code. You don't have to do any weird functions. If you want to increase, add, subtract, multiply, divide, anything here by something specific, then you just say, hey, everything in this column, add to, or whatever, and it'll do it. You can apply custom functions. For instance, one thing I did here is I just took that resistivity column and in ohm meters, and I applied a function to take the to convert that into electrical conductivity, and converted it from ohm meters to millisiemens per meter. And so did dot apply. This lambda x function is something that I think we talked about in the second Python workshop. It's a way to specify that you want to apply that function to each element in a specific data frame, list, array, whatever. So you do lambda x, and then that x is just basically in the following function is the element of that row. So this does that it takes the inverse of each element, multiplies it by 1,000, and returns it. Big thing when you're dealing with the data frames is you have there are two different types of axis directions. Axis equals 0 means you're doing it row wise. Axis equals 1 means you're doing it column wise. So if you want to specify what direction you're applying that function, make sure you're applying it in the right direction. Additionally, you can, if your function doesn't easily return a NumPy array, or doesn't easily, doesn't require a NumPy array as an input, you can use df.map, which you can apply some kind of more specialized function to everything in the data frame. You can also combine or merge based off of you have p.concat, where you specify what data frames or series you want to combine together, and whether you want to combine them based off of their rows, which would be axis equals 0, or by their columns. You can also use merge, which can return if you have two data frames that have maybe a similar column or two between them, and you want to merge them based off of similarities between them, so that you have some combined information. You don't have to bring them together and then delete the duplicate columns. You can use merge that has a whole bunch of conditions based off how you want to combine them, based off what kind of similarities. And then you also have some other random stuff, such as sort values. Sort the values in your column or in a series of data frame based off of specific column values. You can insert columns matching length, matching the length of the data frame at some specific position. I forgot to specify it here, but you can also do pd.uppercase-T to transpose your data frame, so all of your rows become columns and all your columns become rows. Should have specified that because pivot tables are a important thing that are often used with data frame management. So a couple of times best practices. So data frames do use a lot more memory than arrays or lists, because there's so much there's so many additional bells and whistles associated with data frames, and the way you can index and label them, and the functions that exist. If you have if you're using a data frame as like your default data structure, it can build up into a pretty significant load on your computer's memory, especially if you wanted to try and like iterate through a function quickly. So just make sure you aren't creating unnecessary data frames, or if you do, throw them into a function so that the code, your computer doesn't actually have to save the output of that data frame each time. Secondly, anytime you take a subset of an existing data frame, it's going to give you the row indexes, there we go, that it got from your from the original data frame. So make sure you do pd.reset index. That'll make sure that you have those. If you want to treat this as a brand new data frame, you can do that to basically reset the row indices. So now instead of going having it hop around from like 0, 2, 3, 7, 10, whatever, it'll reset everything from 0, 1, 2, 3, 4. Make your column labels simple but descriptive. Having basic X and Y columns are great. If you have something with a very long title, try and see if you can shorten that, or you can store your column names as a list. You can do list df.columns, which will make a list of all the column names, and then you can call the specific column name based off of its position in that list. It's just ways to make sure you don't have to keep typing out a super long column name if you don't have to. Last thing I want to talk about on the Pandas stuff before I kind of quickly go through a example is so as I mentioned back in the differences between data frames and databases, Pandas data frames are optimized for ease of use, but not necessarily for efficiency. It's very versatile and that's a great tool about it, but if you're dealing with incredibly large data files, or if you're trying to iterate a function over a large data frame, it will take a noticeably long time to try and have your computer try and work through it. So there is a package available called Modin, where it's either Modin or Modin. I think it's Modin. It can be installed and basically is used as you basically import it as pandas. You can see in the graphic at the right here, instead of doing import pandas as PD, you do import modin.pandas as PD. And what that does is it will what it'll do is it will it uses a few different types of distributions to basically allow your pandas data frames to utilize some parallel computing support. So if you have a computer that has multiple cores, that has that your CPU has multiple cores, then it is a tool to kind of help to use those so that you have more computing power at your fingertips and can take less time when dealing with large pandas data frames. So it helps. It's there to help improve the efficiency of pandas data frames. The main thing that I'll kind of give a little asterisk for is I use a Windows operating system and use the interactive environment Spider as my main Python coding thing. that combination is a rough, it makes for some rough times of trying to incorporate modern. Python has this global interpreter lock that kind of it's there to stop things from kind of running unnecessarily, or I don't know the specifics of it, but it's one thing that's made that complicates the ability to do any parallel processing in Python. And then Windows operating systems also have some stuff there to complicate things. If you use Linux or a Mac OS, you might have a better time with it. If you use Jupyter Notebook or Python Terminal, tends to operate operate a bit better. Spider, since it's like an interactive environment, kind of gets a bit weird when you try to bring in different CPU workers to parallelize stuff. So it's handy, it's good stuff. That's a good question. How do I know that the feature I'm coding really needs parallel computing and is just not optimized? That is a great question. I had a situation like this fairly recently where I had to basically create a search function to search through these large text files and then switch a certain value at the end of a column if it met a certain condition. These were like million plus length text files. And so I'd say the first things you'll want to do is, if you notice that your code is taking a very long time to run, see what parts of it you can define, you can throw into a function definition. So you basically do like def and then some function name, and then you'd throw your code into there. And what that'll do is it'll when you run it, it won't have your computer save each data structure each time it goes through it. Another thing is, if there are ways where you can move from pandas data frames into NumPy arrays or Python lists or tuples, basically, like, as you move from pandas to NumPy to just basic Python, you increase in the efficiency of your code. Like I said, pandas data frames are great and they have so many capabilities, but if you're able to do the same thing using just NumPy arrays or Python lists, it really will make a noticeable difference in the speed and optimization of your code, especially if you have to iterate over certain things a bunch of times. So I think there's really no surefire way to know whether or not you need parallel computing or if it is just unoptimized until you start, messing around with it and seeing, what happens if I move from a bunch of pandas data frames to NumPy arrays and then throw that into a function to call later. Like, does that improve it enough where, okay, this will do, or do I need to start introducing parallel computing? If you're able to get stuff like Modern working and introduce the parallel computing, it does kind of like increase the threshold of where you start feeling like you need to start optimizing your code. It allows you to kind of get away with being a bit sloppy in that sense. But it is also a bit of a pain to try and it can be a bit of a pain to try and get going, at least if you're very particular about using Spider in a Windows OS like I am. So in the interest of time, I'm going to quickly jump into so let's see. Can pandas data frames be used for calculation of eigenvalues for a column directly without converting to NumPy and using SciPy? So yeah, I think if you wanted to outline the steps required in calculating an eigenvalue without specifically using SciPy, you could do that within your data frame, just like keep using like map or apply functions. I'd say it you would still, as far as like simplicity and readability is concerned, it might still be best to use the SciPy sparse linear algebra eigenfunctions or eigenvalue function. It's you'd have to kind of take it on a case by case basis of whether or not to see what kind of makes the most sense. It even though your data frame will construct will be set up like a matrix, Pandas doesn't have an internal function to calculate the eigenvalue of calculate the eigenvalue of the column or data frame that you're working in. All right, so let's go through this quickly. My GeoPandas presentation is very short, so we are going to do this quickly. So in the pandas folder there, in the folder that I shared, you have this code here and this data file. Basically it's set up so that you can kind of just use it as you go. Just kind of like run each cell independently. The main thing you want to do is just make sure that you change the path of your folder that has the file to whatever it is. If you have it in your downloads folder, make sure you specify that. But we use read CSV, so dealing with just like a basic comma separated value file, reads in the file within the data path. Sometimes depending on on how you got that CSV, it might have some weird encoding, and so I just do this in there because it helps. But if you have an Excel file that you save as like a UTF-8 CSV file, then you really usually don't need this last bit. But as you can see with this data file, let me share this full screen because I think it doesn't. Yeah, there we go. Full screen. Awesome. So with this data frame, it's an ERT data set that I took at one of my sites. You have your electrode positions, resistivity, and a bunch of other data. So first off, if you have any columns that are unnecessary, like this random one on the side here, you do the name of your data frame .drop, specify the name of the column, and then you can create a list of the names of your columns, just so it makes it a little bit easier to reference them. Then I'd specify the index of the resistivity column and use matplotlib to plot it. So the good news about using pandas data frames to plot stuff is just that you have your values of the same length here that are easy to be they're easy to be used, they're easy to be called. So you can have the index of your measurement be like your x-axis, and then specify column as your y, and then just be like, yep, my x is data.index, my y is data is a specific column, and then you get your plot. Now you can see there are some very out of whack resistivity values in here. Took this in a coastal marsh. I should not be getting resistivity values close to 80,000 ohm meters. So we filter, right? Specify that resistivity range. And this is basically going back to that one whatchamacallit, that one slide I had of the different ways that you can apply a filter to a data frame. This is going to run through all of those, right? So you see lose 629 data points that are outside of that specified range. And so now if we did plot that scatter of data row filter dot index, and then data row filter, right? Because that's what we defined this as. Although let's make sure we have it in the right way first before we, right? So plot dot scatter data row filter. Right. You can see we just have values from 0.5 to 1,000. And then this function, this cell just walks through that whole process of creating a column that's now your apparent bulk conductivity values by taking that row filter, that row column from my filtered resistivity data, defining it as a series where it's 1 over the resistivity value times 1,000 to get into millisiemens per meter. We need to rename it. Let me insert it in position 6, which is right after our resistivity value, right? Let's do that. We did pd.concat, where we have the data frame that you want to start with. Cond is the pandas series that we're adding to the end, and then we're adding it as a column and not as what should we call it? Not as a row. And so you can see with we kind of threw it in both ways. So we have it at the end here. That's the concatenated column, and that's the inserted one. So because we are now getting close, I'm going to quickly zoom through this GeoPandas one. Go through the, let's do the actual. There we go. We'll zoom through this, zoom through that second example. If we have any last minute questions, I'll gladly answer them. GeoPandas. GeoPandas basically takes the framework of a pandas data frame and applies map tools, coordinate system conversions, and geometries based off of this other package called Shapely. And the way that Pandas has data frames, GeoPandas has geodata frames, keeping it nice and simple. So it has all the advantages of Pandas as far as ease of use and ease of data selection and querying and manipulation. But now it has this intrinsic support for plotting and geometries. So similar fashion to Pandas, right? If you know the data you want to throw in, you know the specific coordinate system, then you can create your GeoPandas data frame, your geodata frame, whatever, just based off of what you have, or you can read in a file such as a geopackage, a GeoJSON, or a shape file, since those have your basically the same configuration where it has data and then geometry. Furthermore, you can actually, once you have your geodata frame, you can actually write it and export it as any one of these files, a geopackage, a shape file, etc. If you want to easily throw it into QGIS or ArcGIS rather, or something of that sort, so that you can work with it later. Nothing too new to talk about when it comes to selecting data. Pretty similar to pandas. You can do it based off of the index. You can do it based off of the column label. Except now you also have this geometry column, which expresses each of your coordinates as a geometric point, or as a line or polygon if you have things constructed that way. Also similar with pandas, the geodata frames can be queried in a similar sense. You can grab your unique values. You can use Boolean logic to get data points that are within a certain range or outside of a certain range, or drop any duplicate points. And one thing that could definitely be very helpful when it comes to any coordinate-based like GPS data sets is that you can merge or join data frames together, so that you have points with the same coordinates. You can add more information to those, to your geodata frame. That could be useful for stuff later on, or you can concatenate and throw in entirely additional data frames if you have more data to add. Let's say you're just building up a large list of coordinates and data that you got from it, so you can just keep adding on to a main file. But one of the big things that's pretty handy is that it makes it rather simple to make maps with some geospatial awareness. So what you can do is, when you have your geodata frame, it can be plotted as absolute, just directly using this GDF.plot. So GDF just being whatever you named your geodata frame. You specify what column you want to plot to each of the points or each of the geometries. You can specify your color map, your axis specifications, whether you want a legend. In this case, you have some keywords, so you can add a label, set your max and min values, and it'll plot that pretty easily. So let's see, we're just about to do it. All right, let's get this last thing in here. Okay, so let's run through this geodata frames or GeoPandas example. So let's reset that kernel. And all right, I see those variables still there. It's fine. So like with anything else, import your libraries first. Set the path for the folder that has your data. Specify the name of your data file, and then read it in, right? To start the same way, starting off with a normal geodata or a normal pandas data frame. It's doing a fun thing where it is really being picky with this. There we go. Now they're all gone. All right. Cool. So here is our data set. We have X and Y coordinates. These are in UTM. So we, collected with Trimble. We already set what zone we want to use. So we have our easting and our northing. We have a few different measurements of conductivity and resistivity. So we have an electromagnetic data set. And then we have the depths associated with each layer, right? So what you can do is you can take that pandas data frame, use it as the basis for a geodata frame, set what you want the geometry to be. If you don't already have these shapely, geometry points, you can use this function points from x, y, specify what your x coordinates are, what your y coordinates, and then specify the coordinate reference system code that is associated with it. If you're unsure what your code is for whatever coordinate system you're working in, you can do a quick search for it. Just be like, EPSG code for UTM zone 21 north or something, or for WGS 84 pseudo Mercator. They'll have the codes for all of these. So you specify your coordinate system, your geometry, and your data. With that, very basic plot of just here are the points that we have data for. Haven't really thrown anything too fancy in there yet. What we can then do is you can import a TIFF file as your base map. TIFF files tend to have this reference file that is able to define the spatial extents of that file. And you're able to open them, right? So we have a object using this raster IO function or package. So basically it's that. And then what you can do is you can specify the bounds of your base map, set that as your axis so that you make sure that your data snaps into that location. And then this is that line from the presentation where we plot it. And we get this, right? So here's the space map of a field site, Assateague Island. All the coordinates associated with the EM survey that we did. And this, get a line, a color bar associated with it for your legend. Last thing I just wanted to show is that similar with pandas, right? You can specify certain criteria to pull out data from your data frame, right? So we have depths here, which is just a series of all the unique depth values in this column, or I guess in the GDF column, right? So GDF has all the same columns as our normal data file, but it has that geometry file. So all the unique depth values pulled from this are in our depths array. We remove anything that has that NaN value. And then what I do here is if you want to get a plot for each depth to see how that, how that conductivity distribution changes with your depth, then you can iterate over this plot function specifying what connectivity values we want to use. So there's this variable here, GDF depth, that I specify, where we get all of the here we get all of the rows where that depth column equals whichever unique depth value we're on at that point. So if our unique depth value is let's say value equals depth 0, right? So negative 0.823 meters. If we were to do this, right, have that GDF depth value, this now just has all of the points where we have that depth, and all the rows where we have a depth of negative 0.82 meters. And so all this does just iterates over that with each of the unique depth values. You can see it kind of build it as it goes. Right, so as we increase in depth, we're increasing in connectivity because we're in a barrier island, so we're getting more saline water. So that is the main examples I wanted to at least take the time to go over. Like I said, in an ideal world, if we had more time, we'd be able to delve into some more complicated uses of pandas and GeoPandas, while also dealing with doing some using the SQLite package in Python, so you could start to get a little bit of exposure to kind of more SQL adjacent database management. But as you can see, there is so much to potentially do and look at and talk about when it comes to database management in Python. So right now we're essentially just dipping our toes in, and hopefully this at least gotten people started to get a little bit familiar with how to work within pandas and GeoPandas, what some of the pros and cons are between the more loose data structures like the pandas data frames versus SQL strict databases, and then also kind of starting to have a few potential examples of stuff to codes to use for some basic functionality. I'll say if anyone has any lingering questions, feel free to drop them in there, but we are past time now. I think I guess I'll hang out for a couple minutes in case anyone has any questions, but if that is it, I can drop the links again to the Python shared folder. Yep, and that should be it. The recording from today will be available on the SEG YouTube page and the open source software playlist, probably within a few weeks given holidays and whatnot. Thank you so much everyone again for coming to another installment of the open source software series in our third Python workshop. I've been Chris. Thank you, Joshua, for this talk on the basic database management and database information. If you have any questions, feel free to reach out, and thank you so much.